Hello again, Mr. Ivetto back now for lesson 7, the last one in unit 9, our introduction to trigonometry. And today we're going to be talking about radian measure here. So we've been working with degrees throughout this entire unit, and while degrees are probably what you're more used to working with throughout your time as a student learning math here, and they might make a little more sense to you because you know there's 360 degrees in a circle, and you might have a better picture of that. But really the much more natural unit sort of for our trigonometry functions in math are what's called radians, right? And a single radian there, right? Today we're going to talk about how to work with radians, work with our trig functions when we're given radians, and really how to go between degrees and radians because they represent the same quantity more or less. They're just a different sort of unit of it, right? So just like you can convert length from inches to feet, you can also convert angles from being measured in degrees to being measured in what's called a radian here. Of course, when you convert inches to feet, there's a conversion factor. There's a simple ratio. There's 12 inches to 1 foot, right? So if you want to know how many inches are in 6 feet, you just sort of multiply by that ratio, that conversion factor here. You've definitely converted units in your science classes. Right here might be reminiscent of what's called like the factor label method, right? So here's your base quantity. This is your conversion factor here with the two labels of what units they are, right? And you always want to put the unit you're trying to cancel out, the unit you're starting with and trying to get rid of goes in the denominators. That way they cancel out top and bottom and you're just left with the unit you want, inches here, right? And it's going to be the same idea converting between angles and degrees here. We still need a conversion factor. But oftentimes what we do is we leave our results in terms of pi, because pi and circles, they just go hand in hand throughout math. Like I was saying, there's really no better language for it other than like it's sort of just the more natural unit for what we're doing here, which might not make a ton of sense right now, but it is a lot easier to work with and it's very common to see. So we definitely need to know how to work these here. Just a quick little note, what is a radian might be your question here. On a high level, it's really just another unit to measure like degrees in a circle. It's the same quantity as degrees, just sort of another unit length in the same way that feet and inches are, but really what they represent, and there's a nice little animation of this. I'll try to link it to all of you when we come to this, but think about the unit circle. The unit circle has a radius of 1 unit from here to here, right? And a radian is sort of like if you were to take this radius and wrap it around this circle here, if you were sort of like fold it up, that would, however far you would get on that unit circle, that would represent 1 radian. You don't really need to know what that is in order to work with these, but sometimes it's nice to just have a basic picture of what's going on here, right? So let's figure out what our conversion factor actually is now. I'm great at this. So let's think about it. How many degrees are in a circle, right? In any circle, not just this one. We know there's always 360 degrees in a circle, right? And if this is a unit circle, what's the circumference? Well, we know from geometry and from middle school even that the circumference of a circle is 2 pi times the radius here. But if this is the unit circle, the radius is just equal to 1, which means that the circumference is equal to 2 pi here. And this is where that little picture I was mentioning of like wrapping the radius around the circle might sort of make sense, because in a unit circle, there are 2 pi radians, we say. So if we were to do what I was saying before and like sort of wrap this radius around and like we just kept having enough of them, we would get a total of 2 pi of those radians to sort of wrap around. Again, we don't sort of need to remember that. We just need to remember this base conversion factor. But if there are 2 pi radians in a circle and 360 degrees, what that tells us is that 360 degrees is equal to 2 pi radians, right? I haven't written the units. Let me just throw those in. Degrees and rad, we abbreviate it like that. They're dimensionless, so you don't really need to keep them the whole time. But just so we have the sense of what our conversion factor is, there are 2 pi radian for in 360 degrees, or there's 360 degrees in 2 pi radian. They're the same idea there, right? And so we can sort of cancel out a 2 from both of these, and we have, or in other words, that there's 180 degrees in pi radians, right? And there we would have our conversion factor. It's weird to think about it like this, 180 degrees equals pi. So we normally sort of write them as a ratio here. So let's think about this. When we want to convert degrees to radians, think we need to go from degrees to radians. So looking back at this little feet and inches part here, we would have to put the degrees up here, and then the number of degrees we have, like we found 180 degrees down there, and the pi radians up there, the number of radians. And what that comes out to for us, what we need to remember in this case is that when we want to convert degrees to radians, we have to multiply by pi over 180, right? Because that's going to take us from degrees. The units of degrees will cancel out since they're in the denominator, and we'll go to radians since pi is our natural unit for radians there, right? And we want to convert from radians to degrees. Well, it's just going to be the opposite situation. Here we're starting with radians. We need to cancel those out in the denominator, and we need to end up with degrees in the numerator here. So when we want to convert from radians to degrees, what we multiply by is just the reciprocal, 180 over pi. And as long as we can remember those two conversion factors, that's really the only new thing we're adding to this unit here, right? So let's just get some practice converting back and forth just to sort of get our feet wet with this, and we're all pretty well acquainted with it. And then we'll see what I was saying, that this is really the only new thing we've added to our lessons in this case. Everything else we've already worked on in the last few units, like the same way we did with reciprocal functions, where we sort of just added on that one piece where at the end we flip our answer to get the reciprocal. Here we just got to do something at the something extra at the beginning if we start out in radians and want to go to degrees, or if we want to start in degrees and end in radians. All we have to do is convert at the beginning, and then it's the same problem. Anyway, though, let's first just practice converting here. So first off, we want to convert each radian measure to degrees or degree measure to radians. So I'm starting in number 1 from degrees, and I want to go to radians. So all I have to do is multiply by pi over 180, right? And then I'll just actually do this math. I have 330 over 180. Well, I'm going to need my calculator for that. So one moment here. Right, so I need to, I'll use my calculator for this part because I'm not going to do that in my head, but I just got to do 330 over 180. And usually we keep our answer in terms of pi, so we're just going to leave the pi there. It means we're not going to actually multiply by pi. Okay, so we'll see what I mean. Switching now to the calculator, I'm just going to do 330 degrees, where we're starting from, dividing by our conversion factor, 180. And I get this messy looking number, 1.8333 repeating. Normally we like to leave these in terms of a fraction, a rational number here. So remember, just to get your decimal to a fraction, if it can be expressed as such, you hit the math button and then enter, right? Because we want to go to frac, that first one, right? So take our answer to a fraction, we get just 11/6. And the way we would write this answer is that there are 11/6 pi radians in 330 degrees, or in other words, 330 degrees is the same as 11 over 6 times pi radians, okay? And converting back from radians to degrees is exactly the same. We just, not exactly the same, but it's the same process, just with a different conversion factor, right? So in number 2, if I want to take us from radians to degrees, and I know I'm in radians because it's in terms of pi, and again, when we are expressing things in terms of radians, we leave it in terms of pi because it just makes the most sense here. But anyway, I just multiply by my conversion factor, 180 over pi. And of course, the pi's are going to cancel out. And I just have 180 over 3, which is going to give me 60 degrees. Or pi over 3 is the same as 60 degrees here, right? And that's all it's going to be for all of them, right? So in number 6, 135 degrees, I want to put that in radians. So I got to multiply by pi over 180. I'll use my calculator again here, and again I want to leave it in terms of pi, so I'm going to go do 135 divided by 180. I get 0.75, which is just 3/4. Right, so I get that this is equal to 3/4 pi radians here. Right, and the same idea, if we want to state which quadrant the terminal side of each angle lies in, well, with degrees we already know how to handle that, but when it's in terms of radians, it's harder for us to think in how many radians that will be, like where it will end up in the coordinate plane. So all we want to do is just convert to degrees, and then we can use all the same skills we've been working with there. Moving on now to how do we actually use these with our trig functions? Well, just like we've been doing before, we're really just adding one extra piece here. So let's say we have a trig function and we're giving it the measure in radians here, like we have with the example cosine of 5 pi over 3 here. And we want to figure out what that value is. So the first thing we need to do then is just convert our angle from radians to degrees by multiplying by, again, from radians to degrees, we multiply by 180 over pi, okay? So I'll take this one, I'm going to take 5 pi over 3, and I'm going to multiply by 180 over pi. The pi's cancel out just like we want. And then 180 over 3 is 60 times 5 is going to give me 300 degrees, right? And then it's just the same problem that we've done beforehand. Steps 2, 3, and 4, we already know how to solve these. It's just finding exact trig values here, which I think was lesson 4 or lesson 5, right? So cosine of 5 pi over 3 is the same as cosine of 300 degrees, which I know ends up in over here, right, with a reference angle of 60 degrees. We've handled this before, so I'm just kind of going quickly through this one. And we know from our ASTC chart that the cosine is also positive here. So this is going to be equivalent to cosine of 60, our reference angle, and it's positive because we're in the 4th quadrant. And now we use our unit circle or our special right triangles. I'll just sketch one right here. Right, let's say this is the 60, then this has a radical 3, a 1, and a 2. So our cosine of 60 is just equal to 1 over 2, our adjacent side over our hypotenuse. And we've done that before. All right, so just like I was saying, there's just one step at the beginning. You convert from radians to degrees and then just solve the way you've been solving this whole unit. By now, we probably have it down pat because we've just been drilling ourselves and we know how to do this here. Right, so let's take a look at a more complicated one. Let's take a look at number 3. We're going to have to do everything we've done this. We're going to have to do everything we've done throughout the units, throughout this unit in each lesson, just all together now. But it's really just one step from each thing. So the first thing in number 3, I see 13 pi over 6. It's in radians. Well, I'm better at working with degrees, so I'm going to go ahead and convert 13 pi over 6 to radians, to degrees by multiplying by 180 over pi. So this cancels out. 180 over 6 is going to give me 30 times 13. Let's just use the calculator. So 13 over 6 times 180 is going to give me 390. So I get that this is equivalent to 390 degrees, right? So I know now that cosecant of negative 13 pi over 6, this is the same as cosecant of negative 390 degrees. But I don't usually like working with negative numbers, so I'm just going to add 360 to this, right? So plus 360, and I get that the cosecant of negative 390 is exactly the same as cosecant of negative 30 degrees, and again, that's because they're coterminal. I still don't really like working with negatives, but I think it's going to be okay in this point. Let's just draw a little chart for us, right? Negative 30 means we went backwards 30 degrees like that. So we know that this angle is exactly 30. In this case, it's kind of easier for us. It gave us our reference angle even. We'll draw our little ASTC chart just because we're going to need that as well. And let's take a look here. This is the cosecant, which we know goes with, cosecant goes with sine because the cos don't go together, right? So this is equal to 1 over sine of negative 30 degrees. Which we could go ahead and we can add that 360 again, and we can get that this is equivalent to 1 over sine of 330, right? Which is what we found, which is what we'd find if we just added another 360 here to using those coterminal angles and figuring out where we lie. But we would get the little picture that we have that I've just drawn there, right? And now we use our ASTC chart. We see we're in quadrant 4, so the sine is negative. So this is going to be equal to 1 over negative sine of the reference angle we already know is 30 degrees. And then we would use our special right triangles. By now we're pretty good at this though, and we know that sine of 30 is equal to 1/2. So this is equal to 1 over negative 1/2. And now just simplifying this out, I get negative 2. Right? Or in other words, the cosecant of negative 13 pi over 6, after doing all of that, I added the coterminal angles to get something I'm used to. I drew my ASTC chart to find out what the SIGN sign is. I found my reference angle. I associated my cosecant with the sine, its reciprocal function, right? And I found my final answer there. And that's how all of these are going to proceed. No matter what we face, like number 4, it's the same idea as what we just did. We just have the sine now instead of the cosecant. and we have 5 pi over 6 instead of 13 pi over 6, but it's the same idea. Convert to degrees, and then just handle it like we've been doing, which means get the angle between 0 and 360, so we know what we're doing and we know where we are. Then go ahead and find your reference angle, figure out whether you should be positive or negative. If it's a reciprocal function, you need to associate it with its regular function, and then once we've done all that, we'll need the special right triangles or the unit circle, and we'll be able to get this here. So that's all for this lesson as well. The rest of these follow the same as we've been doing, so I'm not going to go over those now. But we will have the solutions and answers provided. At this point, you should be able to handle everything. And remember, it's really just sort of piecing on an additional step to do throughout each of the lessons. But that's all for Unit 9, our Intro to Trig. You'll talk more about trig in Unit 10 and 11. We'll talk about trig a bunch of times, to be honest, but that's all for now. So.